Welcome to our exploration of folding and faulting, the dynamic processes that shape the Earth's crust. At the heart of these phenomena are the powerful forces generated by plate tectonics. Convergent boundaries push rock layers together, causing compression that leads to folding and sometimes faulting. In contrast, divergent boundaries pull rocks apart, resulting in tension and the formation of faults. Shear forces, meanwhile, push rocks in opposite directions, breaking them into subparallel blocks. Understanding these forces is crucial, as they determine whether rocks bend, break, or slide past each other. As we move forward, we'll see how these stresses translate into the fascinating structures we observe in geology, setting the stage for a deeper dive into rock behavior and deformation. Rocks respond to stress in two primary ways: ductile and brittle behavior. When subjected to stress, rocks may bend and flow without breaking, a process known as ductile deformation. This typically happens deep within the Earth, where high temperatures and pressures allow rocks to fold over millions of years. On the other hand, brittle deformation occurs when rocks break suddenly, forming faults. This is common near the Earth's surface, where rocks are cooler and less able to deform plastically. The transition between these behaviors depends on several factors, including the type and amount of stress, temperature, rock composition, duration of stress, and depth. Recognizing these differences helps geologists predict where folds or faults are likely to form, and why certain regions are more prone to earthquakes or mountain building. Folding is a classic result of ductile deformation, where rock layers are compressed and bend without breaking. Two main types of folds are anticlines and synclines. An anticline forms an arch-like structure with the oldest rocks at its core and limbs dipping away from the center. In contrast, a syncline resembles a trough, with the youngest rocks at its center and limbs dipping inward. These folds often occur in pairs, sharing limbs and creating complex patterns in the Earth's crust. The intensity of folding can lead to inclined or even recumbent folds, which play a significant role in mountain building. Understanding fold morphology is essential for geologists and engineers, as it influences everything from resource exploration to the stability of structures built on folded terrains. When rocks can't bend any further, they break, resulting in faults. Faults are classified by the movement of rocks on either side of the fracture. Normal faults occur when the hanging wall moves down relative to the footwall, typically due to tensional forces. Reverse faults, including their low-angle variant called thrust faults, happen when the hanging wall moves up, usually from compressional forces. Strike-slip faults, on the other hand, are caused by shear stress, with rocks sliding past each other horizontally. Famous examples like the San Andreas Fault demonstrate the dramatic effects of strike-slip motion. Fault zones are not just geological curiosities, they represent major zones of weakness, can trigger earthquakes, and influence groundwater flow. Understanding fault types and their mechanics is vital for hazard assessment and safe engineering design. Beyond faults, rocks can also develop joints, fractures where no significant movement has occurred. Joints often form in sets influenced by tectonic stresses, unloading, or cooling of magma. Both faults and joints reduce the strength of rock masses, which is critical for engineering projects like tunnels, dams, and foundations. The Geological Strength Index (GSI) is a tool used to estimate how jointing and faulting affect rock mass strength. Fault zones, in particular, can create hazards by providing pathways for water or acting as zones of weakness that may fail under stress. Proper geological assessment is essential to avoid disasters, as seen in historical dam failures. In summary, understanding the interplay between folding, faulting, and jointing is key to both unraveling Earth's history and ensuring safe engineering practices.